Hello and welcome. So my talk is going to be, as Tsuki said, about V-Ray Next, and more specifically about update 2 that's coming out for 3ds Max. Most of the stuff is not really specific to 3ds Max because it's related to V-Ray itself, and it will go in all the other integrations. Some of it is already in V-Ray for Maya, but it's mostly based on the upcoming update 2 of V-Ray for Max. This is just a list of some of the things that I think are most exciting about this update. I will not go through the whole list, but I picked like a few stories about this update that I wanted to talk about, similar to what I did last year. The first thing that I will spend some time on is the ability of V-Ray to render many light sources. Next, I will talk a little bit about memory tracking, and by that I mean tracking memory usage for rendering. I will talk a little bit about the improvements that we've done to the light cache in V-Ray. And I will quickly go through some V-Ray GPU stuff, just an update. Obviously, there's a lot of other things in this version of V-Ray, so that's what I'm going to talk about is not everything. And hopefully, a little bit after Total Chaos, you'll be able to see all these things and test them for yourself. So the first topic is better handling of scenes with many light sources. And by many, I mean thousands of light sources. We introduced the adaptive lights technique in V-Ray for rendering scenes with many light sources. And it works well, but the result of this, what we found out, is that people just started adding more and more lights to their scenes. So some of the scenes that we got from customers lately have 1,000, 2,000, even 5,000 light sources. And that's something normal. Whereas I was going through various scenes that we've gotten through the years. And initially scenes used to have like maybe 20 or 30 lights. Then they went up to 100, maybe 200. And now scenes routinely have thousands of light sources. So I guess this basically means that if you allow people to do something and make things more complex, they generally do that. So we had the adaptive lights, but they still had some drawbacks. First, they could only work for the final rendering of the image. They could not be used for the light cache, for example, because the adaptive lights require some information about the scene, and they cannot work right away. You need to do a little bit of rendering before they can be useful. And until you get to that point, the rendering could still be slow. Also, sometimes we could miss light sources in some parts of the scenes, which caused flickering or artifacts in the final render. And also, they only work if you use the light cache. If you don't have GI enabled for whatever reason, or you just use brute force GI, we could not use the adaptive lights. And this was occasionally a problem for our users. And initially, when V-Ray was created, we just did the simplest thing. For every shading point, we go through all the light sources in the scene, we evaluate them, and return the results. At some point, we started doing something different. Instead of evaluating all light sources, we were just picking a small number of lights to evaluate. During the light cache calculation, this was about 20% of all light sources in the scene. So for example, if you had 1,000 light sources in the scene, during the light cache calculation, we would only evaluate 200 of those randomly. And during the final render, we would pick an even smaller number, maybe like 8 or 16 light sources. And this kind of works, but obviously as you get more and more light sources, it becomes problematic because we just randomly picked those light sources without any, considering how important they are for the given part of the scene. So it remained like it was obvious that we needed to improve this somehow. So I started looking at, I knew that we would have to do this. So I was keeping track on various papers and approaches that people did. There are 3 papers that I found the most interesting. They are listed on the right side. The first paper was published last year by the Corona guys, and it was about the new hierarchical light solver in Corona. The other paper that I found interesting is about the iRay renderer that was published by NVIDIA, I think 2 years ago. And the third paper was published by Sony Pictures Imageworks last year, and also dealt with scenes with thousands of light sources. And what all these papers had in common was that they organize the lights in some kind of hierarchy in the scene, so that it will be possible for a given shading point to quickly select a number of light sources that are in some way important for that point in the scene. And the papers have different methods to estimate how important the light is based on the intensity of the light source, the type of light source that it is, and so on. And there are also other details. Also, another thing that you could do, and what we have done in V-Ray for a long, long time, every light source has a cut-off threshold parameter that basically allows V-Ray to estimate how bright a light is, or how strongly it affects a given point in the scene, and skip this light altogether for this given point. And we've had this in V-Ray for a long time. It really helps, but you still have to go through all lights sequentially. So we didn't have a hierarchy type of thing. So I looked at these papers, and the obvious thing was that we also needed some kind of hierarchy. But the difference is that we don't need it to be very precise, because for the final rendering, we will still probably be using the adaptive lights, and they work fairly well. So we would ideally only use this hierarchical approach only during the light cache phase. So it was not needed for it to be super accurate. It just needed to be a little bit more intelligent about figuring out which light sources to evaluate. And a large part of these papers deals with making the estimates for the various light sources as precise as possible, but we didn't really need that. And also, because we want this to be usable in V-Ray GPU, the algorithm had to be easy enough to allow us to do that. So we added this light tree structure to V-Ray, and as usual, this was just something in my mind until a customer came along and said, I have this scene that I need to render, and it renders very slowly, and I have these problems with adaptive lights, so can you help me? And I had to, I decided that that's actually a very good opportunity to implement this and test it with a particular scene to see what kind of improvements we can get. So the way that it works, all light sources are classified into 2 types. One is light sources that don't have any definite position in the scene, but are usually infinitely far away, like the dome lights or the sunlight. And everything else, all the light sources that have some position in the scene, are organized in this hierarchical structure, which is basically a binary tree of light sources, which is called a light tree in V-Ray. And for every shading point, we go through all the infinite light sources and sample them, because they are usually just a couple. There's usually just one sunlight or one dome light in the scene, or maybe 1 or 2, but they're just a small number, so we can afford to evaluate all of those infinite light sources. And for all the lights, we traverse this tree, this binary tree, trying to estimate how much each branch of this tree contributes to the shading point. And we only take into account the position of the light source and its bounding box. We don't care about anything else. We don't care about how bright the light source is, what type of light source, orientation, and so on. And we also ignore the material at the shading point, so we just assume that it's some kind of diffuse material. Like I said, it works fine because we don't need an accurate estimate for this. We just need to sort of pick closer light more often than other light sources. It also, very important thing about this light tree is that the one thing that it does assume about light sources is that they have inverse square fall. So for lights that have directionality or some kind of non-physical fall, it still works. It just doesn't produce maybe as optimal results, but it's fine because the final render, like I said, would still be going through the adaptive light, so it works out all right in the end. And here on the right, you can see sort of a schematic view of how this works and when the light tree is being used. In the default settings for V-Ray, when you have brute force rendering at light cache, we use the light tree for the light cache calculation because we can build it in advance and it doesn't require any sampling of the scene. And then we use the light tree to fill in the input to the adaptive lights algorithm, which is used for the final render. And if we don't have the light cache, if we just use brute force rendering, then we just use the light tree itself. It's an unbiased algorithm because it really only modifies the probability for evaluating a light source. It doesn't actually remove light sources from the calculation. It does give us a nice performance boost for the light cache because on average it selects a fewer number of light sources, but they are more important, so you get better results with fewer light evaluations. Also, it's less likely to miss important light sources, so any artifacts or flickering with adaptive lights are reduced quite a lot. It doesn't have any user controls. There are no options for this in V-Ray. It's just completely automatic. And here are some results. This scene is from Evermotion. It has 3,500 light sources. And again, like I compared this to initial scenes from Evermotion from the very first packs, which only had like 15 light sources maximum. And now they've gotten up to 3,000. For a light cache with a little bit higher settings, the full light evaluation, if you at every single point you evaluate all the light sources in the scene, the light cache itself will take 5 minutes, 5.5 minutes. This is without the final rendering, just the light cache calculation. And if we use uniform light selection, what we had in V-Ray 3 and in the initial release of V-Ray Next, this goes down to 1 minute 50 seconds. And with the light tree, which we have now in update 2, this is down to 42 seconds. So that's quite a speed improvement. And for many scenes, it turned out that actually the light cache calculation is a significant portion of the render time, so this actually can save quite a bit. So one final note here for the final rendering is that the light tree changes the way lights are sampled across the image. So this requires an adaptive algorithm for image sampling to make the noise distribution even across the scene. And we'll have an example of this. So this is a final render of another scene. Again, this is an Evermotion scene. And I tend to use those scenes because they are very good for testing, basically. This one has a few hundred light sources. They're not 1,000, but still quite a lot. So this render here is what you would get with V-Ray Next update 1 if you don't have any GI, so there are no adaptive lights, and you do just one sample per pixel. So no adaptive image sampling at all. And it's quite noisy, but the noise is kind of like sort of uniform across the image. This is what we get with the light tree with update 2. And again, this is just one sample per pixel, again, no GI. So this is only the direct illumination. And so we don't have the adaptive lights, but we use the light tree to pick which light source to evaluate. So as you can see that there's quite a bit of a difference. And this is the final render if we enable the adaptive sampling in V-Ray. this is what the sampling rate render element looks like. You can sort of see where the sampling of a light source changes. Like you can sort of see that circle where the light influence is below some threshold or another that causes the light tree to use different sampling. But the adaptive image sampler takes care of this. So for the final result, there's no visible like boundary, no visible edge in the image. And the final render here with update 2 is 1 minute and 38 seconds. Whereas if you try to do the same thing with update 1, you will still get the image, but it will be almost twice as long. So this actually, the light tree by itself helps a lot in this case. And if you look at the sampling rate render element for update 1, it's quite a bit noisy. This is just comparison between update 1 and update 2. So the recap here is that we can render scenes with thousands of light sources much more efficiently. The light cache is also faster. Brute force rendering is also faster. The chances that you get any sort of artifacts or flickering are reduced a lot. This algorithm is present in both V-Ray and V-Ray GPU. There are no user controls, so basically you don't need to worry about it at all, and it's an unbiased algorithm. The next thing that it's actually quite a big feature for us on the development side, even though it's like to the users maybe it looks like something that's not that big of a deal, but for us it was difficult to implement. But basically at some point we realized that it would help a lot our customers if we give them some indication of the memory usage during rendering, like which parts of the scene are taking up the most memory. Was it GI? Was it the frame buffer? Was it some particular piece of geometry or a bitmap? It would basically help people to optimize their scenes. We also realized that this type of information would be very useful for the Chaos Cloud. Obviously, when we run machines in the cloud, we need to specify how much memory they have, and if we have some kind of way to like keep track of the average memory usage, it will help us to maybe allocate resources better on the cloud. And finally, this is a useful tool that can help us catch bugs in V-Ray itself. And actually, this is exactly what happened after this feature was originally implemented. There was a customer scene that, for whatever reason, I noticed that the scene itself was taking about 30 gigabytes to render. And according to the memory usage statistics from V-Ray, 16 gigabytes were taken up by light sources, which is super weird. And we found out that we had not exactly a bug, but an inefficiency there where we just duplicated some large data structure for each light source. And it allowed us to fix this problem. But until I had this memory report, I had no easy way to figure out how this memory is being spent. So I knew this was a problem several years ago, but V-Ray is now a very large code base, so you can't just go through every single memory allocation to describe it and maybe report what kind of memory it is. So we had to find a solution that requires minimal changes to our code. So we had a discussion with various developers, and there were different suggestions, but finally we chose the method that was suggested by Konstantin Petkov, who worked in the Phoenix FD team at that time. So his suggestion was basically to use some kind of tags to tell the memory allocator that within a given scope, everything that is being allocated is related to something in the scene, some kind of object or some kind of specific category. And in the code, this is what it looks like. You have this temporary tag object that you create that describes what that if any memory is being allocated in this scope, it should be related to this specific category that can be reported to the user later on. And on a lower level, we just replace the new and delete implementations that are used by V-Ray and all the V-Ray plugins. We do have functions equivalent to free and malloc, just in case somebody needs to use those. And we provide the implementation of this tag that tells the memory allocator what is going on. The implementation itself was done by another developer, Nikola Yanakiev, which is interesting because Nikola was originally an intern until, well, not very recently, it's been a while now, but originally he was an intern. He worked on a project which was kind of interesting. Originally he was trying to figure out if there's a pattern in which the members of the V-Ray ray context are being accessed so that we can reorder them for better cache locality, which was kind of an interesting project in itself. But anyway, he worked on various little things in 3ds Max, and then Alex Kazanjiev, who is our team lead for 3ds Max, suggested that Nikola should do the memory tracking implementation. And I had my doubts because it's a big change. It affects everything in V-Ray, but it didn't hurt to try, and I decided to see how far we can get with this. And it actually turned out all right. This was actually done. It was not easy. Like, we did a few broken attempts. So several times we pushed the changes, thought everything was okay, and had to revert them after a couple of days. But finally, it's there, it's working. Actually, the implementation of the memory tracker was included in update 2 of V-Ray for 3ds Max. So it's been there all this time, and it seems to be working fine. So now we have just added the reporting capability. The way that it looks, the most obvious thing is that at the end of the render, you get this list of memory usages for V-Ray, and the important thing is that this is peak memory usage. Like, during the render, at the moment the rendering was taking the most memory, this is what it was spent on. So it's not the memory at the end of the rendering, it's the peak memory usage. Obviously, the challenges here were to make this with minimal performance impact. Like, it shouldn't slow the renderer down. Also, it should be as global as possible. It should track all allocations everywhere. And one thing that was super useful in that regard was that we have a build system that allows us to rebuild all of V-Ray very efficiently. We had just relatively recently switched to CMake. Before, we used some kind of homebrew build system based on PHP, but this wouldn't have been possible if we didn't move to CMake. Like, we could only do the memory tracking because we had the build system already in place. Then we needed to figure out a way to store some additional information about every memory operation. Again, we tried a few different things that didn't work out too well, but finally we decided that we should store this information completely separately from the memory blocks themselves in a hash map. And then this had to work with multi-threading. It had to work with V-Ray plugins, not just for V-Ray itself. And also, it had to work with V-Ray itself being a plugin. Like, we usually have V-Ray for 3ds Max, V-Ray for Maya. So our memory reporting and our memory allocator should not clash with whatever the host DCC application is doing. And this was really tricky to get right, not so much in Windows, but on Linux. But finally, we figured out a way to do that. In addition to the messages in the V-Ray log file, you can also get a JSON report or an HTML report if you want to do some kind of parsing of the data. The HTML format is a lot more detailed because it also gives you memory usage for each object in the scene. Like, in this particular case, there's a teapot, and it tells you how much memory is allocated for that. If you have textures, it will tell you how much memory is taken up for a particular texture. and so on. The JSON is really for automatic parsing by tools on a render farm or something else. It's not really designed for humans. So this is controlled from the V-Ray settings. You have in 3ds Max, there's a new section in the system settings about memory tracking. You can turn it on and you can specify where you want the file to be written. In Maya, the same thing, you have a memory tracking section in the settings tab that allows you to do the same thing. And as a result, you get the two files, HTML and JSON, in the folder that was specified. That's it for the memory tracking. I hope that it will be really helpful. And like I said, it actually is useful for us to improve the memory usage in V-Ray itself. The third topic that I wanted to cover is some improvements to the light cache in V-Ray that we implemented for update 2. First, some history. The light cache is one of the oldest pieces of code in V-Ray. It was developed in 2004. And here is on the right, you can see one of the very first images that I rendered with the light cache. It's one of the reasons why V-Ray turned out to be so suitable for architectural visualization, because it gave us a very quick and efficient way to do global illumination with multiple bounces. It has changed over the years, just a little bit, not too much. The basic algorithm remained the same. And it was time for an update. There's no specific paper for the light cache. When I originally developed it, I thought about it as kind of inverse photon mapping thing. And it's essentially a 3D point cloud that stores information about the global illumination in the scene at various points. And the data structure for this is a KD tree. And then last year, there was a paper at SIGGRAPH published by NVIDIA called Fast Path Space Filtering by Geospatial Hashing, which was actually more targeted at real-time global illumination. But it did suggest using a hash map for storing the information instead of a KD tree. And this looked really interesting. I had not thought about this, so we decided to experiment with this approach and see where it went. The first experiment was actually to try and implement this in Lavina. Diane Nicole did this, and it worked really well. I have a video a bit later to show you how that looks. So we decided to put this in V-Ray itself. And the actual algorithm that V-Ray uses is very similar to the path space filtering approach. It's not exactly the same, but similar enough that it was just really a drop-in replacement of the data structure. Just replace the KD tree with a hash map. And basically no other changes. Radoslav did this change in V-Ray and V-Ray GPU as well. And there are a few advantages to a hash map. The first is that it is simpler for storing information and for looking up information. The KD tree is usually stored in some kind of binary data structure. Finding a point in the KD tree is not trivial. It requires a recursive algorithm, and it's not difficult, but there's a lot of overhead associated with it. Looking something up in a hash map is a lot simpler. The other advantage is that the samples are fixed in space. And you will see this clearly in the comparison videos. With the KD tree, because we store points, and depending on exactly how the rays fly through the scene during the light cache, you may end up with the samples being in different places at the different frames of an animation, so you could get flickering. The hash map is a lot more stable in that regard. And finally, the hash map approach is a lot simpler to implement on the GPU. So this is what a light cache looks like, or used to look like in the V-Ray before update 2 and older versions of V-Ray. It's ugly, but you almost never see this directly, so you usually have brute force for the primary G engine, so you don't really see that. But this is what it actually looks like. And this is what the hash map-based approach looks like. And you can see that it looks a lot nicer. And I have a video here to show that. So this is a short animation with the same processing that I used when I originally developed V-Ray, the light cache for V-Ray. So simple animation, there's only the sunlight and environment light, nothing else in terms of light sources, so almost all of the illumination comes from GI. And I don't actually think that you can see it very clearly on the screen here, but you actually get a lot of flickering in this area here. And I hope that maybe this will be visible later on if you watch this on YouTube. But I had some comparisons between the light cache approach and the KD2 approach, so you will have to trust me that one has less flickering than the other. Yeah, this is again the final render. But basically, oh yeah, this is what the light cache used to look like in animation, as you see, because the samples get in different places for every frame, you get kind of a very flickery result. And this is what the hash map based approach looks like. It's still, the samples themselves still flicker a little bit, but at least they are in the same place and they don't jump around from one frame to another. So it's a lot more stable. As I said, we also implemented this in Lavina, and this is what it looks like. Again, the same expose the scene, export it as a V-Ray scene file, and load it into Lavina. Looks like this. This render here uses the denoising and brute force rendering as a primary engine, and the light cache is a secondary one, but I just wanted to, and we'll see the light cache itself in a bit. This is just the original camera move that we had in the scene. It's exported in the V-Ray scene file, so you also get this in Lavina. But at any time, you can just pause the animation and then you can walk around the scene, which is what I'm doing here. And here I'm turning on the light cache for both primary and secondary pulses, then turn off the denoiser, and this is what the light cache looks like. And you can see that it's being filled in while I'm moving around the scene. And obviously the black areas are places where we don't have enough samples yet for a stable result, but if you add the primary brute force pulse into the denoiser on top, you don't really see this. This is using brute force for the primary pulses. And then getting the denoiser back on. All right. So in the new version of V-Ray for update 2, in the light cache settings, you get this new parameter called type, and you can switch between the old KD2 implementation and the hashmap version. The hashmap method will be the default for new scenes. We just kept the old method there for compatibility reasons for old scenes, but eventually we want to remove it. We implemented the hash map approach in V-Ray GPU as well, and actually on the GPU, it's the only method that we use. We don't have both approaches there. It's only the hash map. And speaking about V-Ray GPU, we did several things that people really wanted. The L surface material and the distance texture were two of the most highly requested features for V-Ray GPU, so now they are there and they work. We also implemented the curvature texture, and after we did support for crypto mats, we used the same approach to implement deep output as well. For the deep output, I'm not entirely sure that it will be ready in time for update 2. It's working in our internal builds, but we have to figure out if it's stable enough to go out in the release, or maybe it will come up in the next update. At the same time, we continue our work on RTX support. I know that we've been saying this for a long time now, and it's not very easy for us to do this, not only because we have to rewrite basically portions of V-Ray GPU in order to support RTX, but also because the RTX API is evolving in a good way, but we still have to do a lot of changes. And it's still, hopefully now it's stable enough that we can focus on V-Ray and getting up to speed, but up until this point, there was a lot of stuff that didn't really depend on us. At the same time, some of the features that we did for V-Ray CPU were also implemented in V-Ray GPU, like the light tree and the hash map based light cache. We are also moving on to our next architecture for V-Ray GPU. So the original implementation, which we called Kernel 1, it's the very first implementation of V-Ray GPU that we had in V-Ray 3 and the earlier versions. And it worked fine, but it was not the most efficient thing you could do on a GPU. So for V-Ray Next, we implemented a new architecture called Kernel 2, which gave us on average twice the performance. And it allows us to do on-demand textures, which helps with GPU memory usage quite a bit. And to get out of core geometry, we need to implement a new architecture, which we call Kernel 3. It's working internally. We just have to make sure that it's stable for everybody to use. There was a problem in V-Ray that people complained about for a long time, which is that if you have a very fine bump map, strong bump map, you get this harsh shadow on the objects. It's not a polygonal artifact. These renders are done with a perfect sphere, so it's actually very smooth. But you get this very sharp transition from light to shadow, which doesn't look too good. And obviously, users complained about this. And I didn't really know how to fix this for a long time, but NVIDIA put together this Ray Tracing Gems book, which they announced at GTC this year. And actually, it has a solution for this problem, which was provided by people working for Sony Pictures ImageWorks. So, and the idea is more or less simple. The contribution from light sources needs to be darker whenever the bump map is too strong. And this works really well. As you can see, the result here is really smooth. And my problem with this was that the change, even though it's small, had to be done in a lot of places in V-Ray. So yes, it's a couple of lines, but they have to be implemented properly in several places so that things like render elements and reflections and lighting, everything works correctly. And also, there was some unexpected problems, for example, with rounded edges, because yes, you need to darken the light contributions for bump maps, but not for the rounded corners. And we needed to figure out a way to make those two things work together, which was not the easiest thing to do. But what helped me a lot, okay, so yeah, just a few words about the ray tracing gems. It's actually a very useful resource. It's targeted mostly at real-time ray tracing, but a lot of the stuff there is actually completely valid even for a normal ray tracer. Also, most of the source code is available. Not all of it, but most of it is available. So it's really helpful. So what I found useful when implementing this feature is the test system that we had set up throughout the years. And I just wanted to mention a few words about it. It's we have a lot of products. There's V-Ray for Max, Maya, Houdini. We also have lots of others. And also, even within a single product, we have several ways to use the render. There's V-Ray, but there's also V-Ray GPU. We have production rendering, but we also have interactive rendering. And we have many developers working on the same piece of code. So it's very easy for things to break. And they break all the time in our nightly builds. That's why we don't recommend people to actually use them. But keeping the product stable whenever we decide to make a release is not an easy job. Like, we realized very early on that just working on the product until a short time before the release and then trying to spend like maybe a month or so to stabilize the product and fix bugs, this is not really working. We have to make sure that everything is at any point of time as bug-free as possible. So originally I had a bunch of scenes that I used to render for every release, like maybe 200 scenes that I had collected from customers or created myself to test V-Ray, and I just ran them before every release. But at some point, like I said, we realized this is not actually feasible if you want stable products, so we had to automate all of this. So we have a small farm, a build farm, the same way that you have render farm that produces animations. We have a build farm that produces builds and also runs the tests for those builds. And this has to be done with various operating systems. Obviously, we need to be able to run 3ds Max, Maya on it. And it also handles all the releases that we do. Like, we have maybe 50 or so builds that have to be done every night, and they have to be tested, run through all the tests. And all this needs to happen in a distributed manner. Like, if we have to wait for all the tests to happen on just a single machine, that's not possible. So we need to do this in a distributed way. The GPU testing is a little bit more complicated because we don't have GPUs in all of those machines, but we still have a couple of them that we use for GPU tests. And the result of all those tests is actually represented in this test viewer system that we also wrote in-house, which renders after a scene is rendered, it compares the result to some reference image that we marked as the correct image for this scene. And our QA team can look at this and figure out what are the differences if something broke, and they can go to the developer and tell them, hey, you broke this since yesterday, can you fix it? And this is what happened when I implemented the bump shadows terminator feature. Things broke. Like in this case, you see exactly that the test scene for the rounded edges texture came out different. So they came to me and said, well, we have to fix this. So I had to figure out how to do it. There is actually a very useful talk by Uncle Bob on test-driven development, which I put here just because it's useful to watch in general. And that was it from me.